All right, guys, welcome back to Loving the Physics. We're now ready for lesson 2. Now, we've done Newton's laws, and we're going to use those laws all the way through this unit. We're just going to now get introduced to different kinds of forces. And the first one, our most straightforward, is the force of gravity. Now, it turns out another name for the force of gravity is the weight of the object. And so if you ever see the word weight, think Fg. And the formula for Fg is right on the formula sheet. It's Fg is equal to mg. And of course, m will be the mass in kilograms, and g on Earth will be 9.81. So the equation is very straightforward. But keep in mind, if you see the word weight, I'll just highlight here. If you ever see the word weight, think Fg. Now, we're always asked as physics teachers to make sure you know the difference between mass versus weight. Because mass is how much material or matter is in the object, whereas weight is Fg. To make sure this is clear for you, let's take a look at a particular object, like an object with a mass of 5 kilograms, and we take that object and we bring it over to the moon. So the moon has the exact same object. We have to realize that when you bring it to the moon, the matter is still the same. It's still going to have a mass of 5 kilograms. It has the same mass because it has the same amount of atoms inside. So that's fixed. But when it comes to the weight, they're different. Because weight, again, anytime you see the word weight, think Fg equal to mg. And now we end up having 5, and the first one, 5 times 9.81. And so when we calculate 5 times 9.81, we get about 49.05. So about 49 newtons-ish. As opposed to when you're on the moon, the weight, maybe I won't use that. That's Fg would be equal to, in this case, the same mass, but a much smaller gravity. It's only a gravity of 1.6. And that comes out to be about 8 newtons. And you can see that it's a lot lighter on the moon, which shouldn't surprise you at all. So, same mass, but different weights. Because weight is a force of gravity. Good. Okay, now before we do our example that involves Fg, I'm now going to show you guys a more advanced way of doing the math in this area. So let me give you guys an example. Let's imagine that we have an object. This is just an illustration, you guys. So just an e.g. You do not necessarily have to write this down if you don't want to. But let's imagine that we actually throw an object up. With a force of, let's say, 100 newtons. And let's say the object has a mass of, let's say, 11 kilograms. And let's make it 400 newtons. We throw an object up with a force of 400 newtons. We'll assume there's no air resistance. Our job, what's the acceleration, for example? Okay, apologize for the messy writing. Now, we know that what we do typically is we draw a force diagram for this. So here's the object that has a mass of 11 kilograms, if you want to write that in there. Now, it's thrown up with a force of 400 newtons. So there's an upward applied force on this object. And this force F would be, in this case, 400 newtons. But it's a vertical situation. And what vertical force do we all experience? And that's the force of gravity. So it's also going to have a force of gravity going downward. There's our Fg equal to mg. And this is going to cause this thing to accelerate upward. And our job is to figure out what that acceleration happens to be. Now, which law? So this is going to be Newton's second law. And that's going to be F net equal to ma. Now, up till now, the method we've been using looks like this. We'd say, okay, let's add the forces together. So there's F plus Fg equal to ma. And then we put a reference system on here, typical strategy. Let's say up is positive, down is negative. But what I want to show you now, and no need to write this part down, is I want to show you this notation. When you actually show a vector like this, you have to realize that the arrow, logically, represents the direction. And the letter represents the magnitude, or how big it is. And so together they form a complete vector quantity, both magnitude and direction. But please understand that the letter F is just the magnitude, and the arrow is the direction. And we're going to use that now to kind of modify our method a little bit. Watch what happens now. On the next level, I'm going to write down the magnitude of F, which is just F without an arrow. And for the arrow, can you see that F is going upward? And that's positive direction. So we can call this positive F. And that shows the magnitude and the direction. Magnitude F, direction positive. Let's do the same thing for Fg. Fg, the magnitude would be Fg with no arrow on the top. The direction is going down, so it'll be negative. Magnitude, direction. M is a scalar, so forget about that. And A is also a vector. So the magnitude would be A, and the direction you can see is upward. That would also be positive. Now, if we simplify this, this will become F minus Fg equal to ma. And what you have to realize is, and I'm just going to highlight that, all of these that you're seeing, these are all magnitude only now. In other words, all those values must now be positive. You don't ever put a negative for any of those. We have already shown the directions in the previous line. There's the directions, which means we never have to show direction again. It's already been done. Now we have just the magnitudes. Okay, I think I can erase this part. Okay. And so I just want to show you, I'm not going to solve the question. I just want to show you how we would take this thing on. Now, how much work do we need to show in the future? It turns out that once you get used to this method, you don't have to show these two lines right here. None of these will be required. You can go straight from F net as ma down to the next line. And you just show the magnitude as the letters and the directions as positive or negative. So we're going to go straight from here to here. Okay, so this is new stuff. Let's give it a try. So you have this question right here in your workbook. Can I get you guys to draw a force diagram and tell me which law this is? Okay, so here's our object. It's being pulled up with a force of 8.7 newtons. So this force going upward, we'll just call it F, is 8.7 newtons. And it's moving upward at a constant 6 meters per second. So I'll put that on the side here somewhere, that the velocity is going upward. Don't draw it as a solid arrow, dotted arrow on the side, like away from the diagram. It's a vertical motion question, so we must include FG. Here's our FG equal to mg is what I recommend. And then we're looking for air resistance. Now, if it's moving upward, which way would air resistance go? And it would go downward. And there's FAR. There's a complete force diagram. Good. Next, which law? Well, if it's going at a constant velocity, that means the acceleration will be equal to 0. And that represents Newton's first law. And that means if we find the net force, that'll be equal to 0. Now, can I get you guys to try to do the next line without showing arrows and showing the positive and negatives? And we'll use the same reference system. We'll choose up as positive and down as negative. So do the next equation line, show just the letters and the positive and negatives. Okay, so we start with F. Here's the letter F. That's the magnitude. Direction, do you guys agree? It's going upward, it's positive. So you can just leave it as F. FG is going down, so that'll be a negative FG. And FAR is going down, so it'll be a negative FAR equal to 0. Now, if you're wondering why we do this method, why can't we just stick with the arrow technique? Watch this. I'm going to take the two negative vector values and put them to the other side. And we discover that F becomes equal to FG plus FAR. Does this make sense to you? And you don't have to write this down, but I'm going to tell you that F represents the upward force, and FG and FAR represent the downward forces. And can you see that the sum of the upward forces must be equal to the sum of the downward forces? And therefore, we call these forces balanced. The forces balance out. Whatever goes up also goes down, so they all cancel each other out. If that makes sense, that's awesome. That's what we want you to do. We want you to understand your force diagram. So this is why this is a very nice way of doing the method, because it helps you compare the magnitudes of the forces. Okay, I'm going to get rid of all that. And now we're ready to solve the question. So we're looking for FAR. Let's get it by itself now. And FG is mg. Okay, now equal to F. Now we know that F is 8.7 minus m. Did you guys notice how the mass was 350 grams? But we don't want grams. We want kilograms. So that's going to be 0.35 kilograms. Last, G. Is G going to be positive or negative 9.81? Now the key idea, this is actually a crucial moment here. Notice that there is no arrow on the top of G. That means that this quantity I'm showing you is only the magnitude of G. And that means it'll be positive value of 9.81. Don't just put a negative 9.81 because you always have. The negative has already been shown. If I go back up, in this line right here, the negatives have already been shown. Don't do it again. So now we can finish it up. So we get about 5.3 newtons. And based on the diagram, you notice how the answer comes out positive and people freak out because but I thought FAR is going down, so shouldn't it be negative? But remember, this only represents the magnitude of the force. That's the magnitude. The direction is shown on the diagram, going down. It doesn't come from the sign. It just comes from the diagram and our understanding. Good? So I encourage you to please try this method in the homework for a while. Get used to it because we're going to use this method for the rest of the course. I'll see you in the next part.